Right, so now that we've seen functions, we're going to start looking at a few different ways to employ them in our program. We've already seen how functions can improve the organization of our programs. We can use decomposition, we can use abstraction to increase our ability to organize and read the programs. Another thing that we can take advantage of now that we understand functions is a concept called recursion, which lends itself really nicely to programming. Recursion actually exists in all sorts of real world examples. So a good example of this is the definition of a U.S. citizen, and I simplified it a little bit, but the essence of the definition is that you're a U.S. citizen if you were born in the United States, um, and if you were not born in the United States, then we'd have to look at your parents. And if your parents are both U.S. citizens, then you are a U.S. citizen. Now, the interesting thing about this is that you notice that this is sort of the cascading question, right? If you're not born in the U.S., then we need to figure out whether your parents are. And if your parents are both born in the U.S., then the question's solved, right? We know the answer. But if your parents were not born in the U.S., then we need to look at their grandparents, right? And so we're looking at 4 different people. And if all 4 were born in the U.S., then we're done. But if maybe even one of those grandparents were not, then we need to go back and look at their parents, right? And so it sort of extends through generations. The idea here, though, is that we're answering the question, are you a U.S. citizen, by rephrasing it and finding out if other people are U.S. citizens. Right? That's an important concept. Um, Moving a little bit closer to the way we'll end up programming this, we can see 2 cases. One is a base case. If you were born in the United States, it doesn't make a difference where your parents were born. You are a U.S. citizen. This is the base case. You can objectively decide this without any further complications. It's important to identify that. Second, we've got a recursive step. All right, so recursion refers to answering a question by asking the same question with different input. Right? So this is the recursive step, and this could cascade sort of indefinitely, I guess. Recursion in programming is implemented by having a function call itself, or maybe usually directly, but possibly indirectly. And when I say indirectly, I mean having a function A call function B, which then calls function A. But more common when we use recursion, we're directly calling the same function over and over again within itself. There are really no problems that absolutely require you to use this strategy, but it turns out that lots of times problems are actually given to us using these recursive definitions, and a lot of times problems are a little bit easier to think about and to at least get our first implementation done if we employ this strategy. So when we're confronted with a problem, one of the things that we need to think about is this a problem that we can solve by breaking it into smaller pieces, breaking the inputs into smaller pieces, and then reassembling the outputs. Right? So if that's the case, then recursion can sometimes be useful. We're going to need to identify the base case. Right? We're going to need to identify a step that we can immediately return an answer without recursion. You cannot employ recursion indefinitely. You have to find a base case. Next, identify a method of breaking the other cases up into smaller problems. Right. So again, in terms of the U.S. citizen example, that sort of falls apart because it's probably not any easier to determine whether parents are U.S. citizens than it was for an additional person. But we're sort of moving towards an eventual base case. Right? So the decomposition should move towards a base case. So I'm going to give you a more concrete example, and then there's a lot of programming exercises associated with this module that'll continue to reinforce how to design these algorithms. N factorial. N factorial sometimes is defined, and I'll write it out here. You can define N factorial as N times N minus 1 times N minus 2 times N minus 3 all the way out, right? Continuing, but it's sort of this never-ending equation. 4 factorial, in other words, is equal to 4 times 3 times 2 times 1. Mathematicians generally define factorial using an inductive definition. The inductive definition is actually really just a recursive definition. The factorial of 1 is defined. It's the base case. We can objectively just say it's 1. And then there's a recursive step that says the factorial of n plus 1 is equal to n plus 1 times whatever the factorial of n is. Put another way here, the factorial of 4 factorial is equal to 4 times 3 factorial. And the factorial of 3 factorial, or I'm sorry, the answer to 3 factorial is just 3 times 2 factorial. Right? And so that's sort of the way the definition is commonly shown. So we can absolutely write a function that behaves this way. Right? We have our base case, 1 factorial, and we have our recursive step, right, where we can calculate the factorial of n plus 1 by recalling the factorial function that we develop with n, which is simply n. So let's go about doing that. So I'm going to ask the user for a value n, and we'll just use integers here because factorials are going to get really, really large actually. And it's kind of a nice property of Python in that integers can be of arbitrary size. Basically, we can use any large number in integers. There's no maximum, and that's something that Python just provides for us. It does a lot of work behind the scenes to make that possible. If we use floating point values are more limited in terms of the actual range of values that we can employ. So I'm going to keep everything as ints. I'll ask the user for this. Please enter n. And I'll just say f equals factorial of n. And I'll print out that n factorial is equal to f. All right, so I'm going to write this factorial function. Okay, so we have our base case. If n is equal to 1, we're going to return 1. No questions asked. Else, we're going to return n times the factorial of n minus 1. Right, there's the recursive step. So let's go ahead and run this and just make sure it works before we dissect it and see actually how it works. So I'll switch over to my lecture folder and we'll run factorial. And let's just type in factorial of 5. The 5 times 4 times 3 times 2 times 1 is indeed 120, so that's looking about right. Let's put some print statements in here just to get a feel for how this is working. So I'm going to print it. I'm going to call a print function here. Factorial of n called. Okay, so let's put that in there. Let's run it again. All right, and we see that factorial of 5 is called, and then factorial of 4 is called, 3, 2, and 1. Right? That's pretty obvious. Let's also put in the fact that we're returning. So I'm going to identify right before I'm returning from this factorial function. Now over here I got to be a little bit more tricky here because I don't want to print this out before I actually make the function call. So I'm going to take this out and I'm going to say retval equals, and I'll return retval because I want this to print out right when I'm about to return, not right when I'm about to make a recursive call. So let's do this again. And so now we can really start to trace this. And notice that the order in which they're called, they're finishing in the reverse order. So let's just trace it. When we call factorial of 5, because the user types in fact of 5, when we call factorial of 5, we go into this function. N's not equal to 1, so we go down here and we call retval, we call factorial of 4. And that's where that factorial 4 is. Notice that when we call factorial 4, we don't immediately proceed to start printing out returning from factorial 5. We're not going to complete this line of code until factorial 4 is completed. So when factorial 4 is called, it's not 1, so it's going to go in here, and it's going to call factorial 3. Factorial 3 is called. Factorial 3 goes in, right? We're going to call factorial of 2. Factorial of 2 goes through this function, we're going to call factorial of 1. And now when we call fact of 1, n is equal to 1, and we'll call returning. And that's why we see factorial 1 called, and then it returns immediately. There's no recursive case in this step. Once we return from factorial 1's call, we have to think, well, which function called factorial of 1? It was when we called factorial of 2. So now that the factorial of 1 returns, we multiply it by 2, and we print out returning factorial 2. So it's kind of confusing. You want to almost think about, just this whole thing sort of starting to unwind itself. Once factorial 2 returns, the code here, when we called factorial 3, can now complete, and we'll print out returning from factorial 3, 4, and eventually 5. Okay, so I want to clean up this function so we can use it a little bit more later. I'm going to kind of undo those print statements that I put in. And I want to take some time to talk about some of the advantages and then also a little bit of the disadvantages of using an approach like this. So there's no question that recursion the first time you see it can be a little tricky, a little confusing, but generally there are a certain class of programs or a certain class of problems that can be really easily and succinctly stated as a recursive call. The only issue that we need to be aware of is that recursion tends to be a little bit of expensive. In the last module we saw, we kept track of call stacks, and we kept track of all the variables that get created when we make these function calls. And one of the things we should recognize is that that takes time. That takes time for the program, the Python interpreter, to create stack frames. Notice also, and if we go back to this terminal, when we call factorial 4, that did not, or factorial 5, that didn't actually immediately return. At the point where we called factorial 1, we had many outstanding call stacks, right? We had a kind of a growing call stack. Now, if we called this with like factorial 1000, that call stack is going to start to get very, very, very large, and there's lots of overhead that's going to be starting to be introduced. So too many recursive calls can actually cause us to run out of memory. It could cause an overflow in terms of the number of outstanding function calls that we have. Our factorial example is actually very, very susceptible to this. If we run this program again, if we do something like 500, notice we get a gigantic number, right? Factorials are 500 times 499 times 498. It's a very, very large number. That works, but if we do like 1,000, in fact, we get an error, and it says maximum recursion depth exceeded. So at some point, we might not really be able to employ recursion for very large numbers. There are other algorithms that actually, if we think about the factorial, each call to factorial is successfully getting smaller by 1. There are other algorithms that break the input in half. Generally speaking, those will always be robust against those type of errors in terms of maximum recursion depth. But the question is, well, could we calculate n factorial without recursion? And the answer is certainly, right? We can certainly do that. If we create another function, fact iteratively meaning a loop, I can certainly just say, retval equals 1 and do simple accumulation. Right? And I can do, I could just do a for loop, right? I in range 2 to n, and retval times equal I. And I'll return retval. So in this case, if n is 1, retval will be 1. We're creating a range from 2 to 1, and that's going to be invalid. That's going to be an empty range. We'll be done. And if we input an n of anything greater, we'll start with 1, and we're basically accumulating a product. So let's call f equals factorial iteratively. And they'll differentiate. We of course want to make sure they're exactly the same. Maybe make sure we didn't make any errors there. So let's run this, and let's keep it simple first. Oops, looks like we did mess up actually. I got 24, and I'm only getting, I got 120 for the recursive and 24 for the iteratively. That's because my range is going from 2 to n, but remember range is exclusive, it's not inclusive. So actually I have to go +1. Let's see how that rolls. Okay, so now we've got the same number. Well, let's make a comparison of this. So first off, if I do, actually, let me quit that. If I comment out the recursive call, I should be able to get the 1,000, the n factorial of the 1,000 factorial to work with the iterative approach. It's again a fantastically large number, but it works because the recursion is not going on, right? I haven't broken that recursion depth with my iterative function. I only call fact iterative once. It iterates a whole bunch of times. I can also look at the actual time cost. So I'm going to import a package called time, and we're going to talk about modules actually in the next few sections of this course. But the time package allows you to get the number of seconds at a very, very high resolution since an arbitrary date in the past. So if I say start equals time dot time, that's actually returning the number of seconds, again at a very high resolution, since January 1st, 1970. January 1st, 1970 is sort of this completely arbitrary but standardized beginning date that all computer operating system clock times are supposed to basically reference from. There's sort of a historical backstory with that we'll kind of stay away from right now, but it's basically this function is always going to give us an increasing number. So if I call start and then call factorial, if I call time and then call factorial, and then I call time again, end minus start is the number of seconds that have elapsed. So I'll add in that, and I'll also put in my timing here. So time.time. So I'm recording the start time. I'm recording the end time. And I'm printing the results out. So I won't use 1,000 because I know that the recursive definition won't go that far. But if I do maybe 500, we can see, let me bring the rest, we can actually see that there is a discernible time difference. The iterative process took about 3/10,000ths of a second, and the recursive process took about double the time. Certainly not that much time. The difference, the delta in these times are not that crazy. But a doubling of the time, if you call factorial enough, if you call factorial over and over and over again in your program, that could actually add up, right? And so the recursive, you can see sort of firsthand that the recursive function call does have an inherent cost associated with it. Now, for factorial, I'd argue that this is pretty much as simple as this. But for other problems, which you'll see in terms of binary search, things like that, the solution using recursion is much easier to write than the iterative approach. And you've got a much more complicated decision on your hands as to which one to use.